Okay, I want to discuss a little bit about why for a rotating object, the direction of the angular velocity omega vector is chosen in the direction it is. Now, we had shown, I had a rotating object here. We talked about the right-hand rule, okay? So this object is rotating, We said you grab the axis of rotation such that your fingers curl in the direction it's rotating, your thumb points up. Okay, and the direction of your thumb gives you the direction of the angular velocity omega. Okay, so I want to talk about why that is, okay, and why that decision is made. Okay, so here I have a rotating wheel. Okay, so this wheel will be rotating in that direction. So we might draw in the previous diagrams, we say, okay, it's rotating. So this little arrow shows that it's rotating. Looking at the screen, this would be counterclockwise. Okay, again, so we don't want to use clockwise and counterclockwise because if you're on the other side of the wheel behind the screen, it'd be rotating clockwise. Okay, so this just shows that it's rotating. All right, and then here I drew a side view. Okay, so on both these pictures, I have some mass here. Let's say that's a chunk of the wheel, okay? And each point of the wheel is moving in a different direction. So piece M1, okay, is headed in that direction. Number 2 is headed up. Number 3 is headed in its direction, right? So remember, these velocities are tangent, okay, 90 degrees to the radius, right? And so I just drew the exact same picture over here now as a side view. So this picture, this is the axis of rotation, okay? That would be in and out of the page. This, okay, this picture here, that's the axis of rotation, okay? So in this picture here, I drew the exact same masses, my M1, my M2, whoops, here's my M3, okay? And as the wheel rotates, okay, so as the wheel rotates with some angular speed, that's my angular speed, omega, each of these little masses is headed in a different direction. So mass number 1 has a velocity in that direction, okay, perpendicular to the direction it's going. Number 2 is headed in that direction. Number 3 is headed in that direction, okay? So each mass is traveling in a totally different direction, okay? So if I drew 50 masses on this wheel, they're all headed in different directions, okay? So what direction is common to every point, to every of those 50 masses on the rotating wheel? Okay, well, either up or down, meaning in a direction that's perpendicular. That symbol means perpendicular to the plane of rotation. Okay, so the direction that's perpendicular to the plane of rotation, that's the axis of rotation. So I'm going to pick the direction of the angular velocity to be along the axis of rotation. Well, do I pick up or do I pick down? Okay, because the axis is a vertical line on this page, so either up or down. The choice to pick up or down is based on the right-hand rule, okay? And remember, the right-hand rule works for right-handed threads. So here you have a screw, okay, has right-handed threads. Here you have a light bulb that has right-handed threads. So if you grab the light bulb with your hand and you twist the light bulb, okay, as shown here. So think of the light bulb as twisting around with some angular speed omega, okay? So think of each little chunk of that light bulb moving like these little chunks of mass over here. So as the light bulb twists around as shown here, okay, which way does the light bulb eventually move? It moves up out of the socket, okay? So you have the socket down here, okay? So think of the right-hand rule working for right-handed threads. So that's what this picture is over here. I have little chunks of mass here. They're all headed in different directions. What direction is common to all of those? Okay, a direction that's perpendicular to the plane of rotation. So the axis is a vertical line. So to pick a direction perpendicular to the plane of rotation, we choose that based on the right-hand rule. Okay, so fingers curl around the axis of rotation, thumb points up in the direction of omega. So that's why omega is chosen to be up. It's based on the right-hand threadedness of the axis of rotation. And the other thing that we'll see about the right-hand rule is that if I take this light bulb, okay, and let's say it's screwed into a socket in the XY plane. Let's say the XY plane is the table, okay? And if you take this hand to unscrew the light bulb, so I didn't draw the thumb there. Well, there's the thumb, okay, and the fingers go around like that. Okay, so if you take your hand to twist the light bulb, just like it's being twisted here, okay, think about the light bulb rotating in the XY plane, okay, and the light bulb moves up in the Z direction, okay. So we'll also see when we get to the subject of torque that the XYZ, okay, that Cartesian coordinate system is a right-handed coordinate system. When you take something so like the x-axis and you start twisting it along the y, okay, that light bulb is going to move in the z direction.